Welcome to Aerodynamics in Minutes. In this video, we are going to see what is an entropy. It may be a bit confusing because there are so many explanations by so many people about the entropy. Let us look. Before going to understand about the entropy, let us see what is first law of thermodynamics says. The first law of thermodynamics says energy is always conserved and energy can neither be created nor be destroyed, but it can change from one form to another. By first law, the phase of water can be changed from ice to water and water to ice without any loss in energy. And a mixing of hot and cold water can be undone. But we know that these things are very difficult to undone in real life. Water cannot be converted into ice without an heat engine. And the first law doesn't explain the spontaneity of the process. For example, if I set fire to a paper, it will be burning without any further requirement of energy. In fact, it releases energy. Let us consider a real world example, ice to water. I took a container and I placed a thermometer inside a container and I put some ice cubes inside it. After some time, the ice cube will start melting. Even though the ice cube is extracting heat from the surrounding, the thermometer measures the same temperature until the final piece of ice melts. Okay, where does the energy absorbed by the ice goes? And we are in a situation we cannot utilize the heat supplied. It is utilized for phase transition of water, ice to water. Therefore, we need something to measure this unusability of energy. And here comes the entropy. There are so many definitions for entropy, but these are the definition that makes more sense to me. They are: entropy is a measure of how much energy is not available to do work. The entropy of a system can be measured of its disorderness. Entropy gives the direction of reaction or direction of flow of energy. And the formula for the entropy is change in entropy is equal to change in heat supplied and heat absorbed divided by temperature. To get the intuition, let us take the ice cube example. The ice cube is absorbing energy from the surrounding, but the temperature remains constant. We know that heat is added to the ice. There is a change in heat added, delta Q. But notice that the temperature remains constant. In ice case, the heat absorbed is converted into entropy. Okay, and it will not be in all cases. In some cases, temperature will change in addition to the heat we supplied. In that case, we need to integrate to find the entropy. For a reversible process, the change in entropy is always zero. You may ask why. The change in entropy was proved to be mathematically zero using the Carnot engine. You can see the proof if you want. I will leave a link in the description. But intuitively, we can say, consider a cyclic process. In the process, if I lost some energy as entropy, in that case, I will not be in the same initial state at the end of the process. You can easily understand that. I will not, if some of the energy is conserved as entropy, I will not be in the same initial state at the end of the process. Okay, therefore the process cannot be a reversible process in that case. Now we can tell the change in entropy for reversible process must be zero. No process in nature is completely reversible. There is always an increase in entropy, but theoretically isothermal, frictionless, oscillating compression and expanding gas is a reversible process. It's a reversible process. One of the example of a reversible process. The entropy of a system always increases. Most of us say entropy of a system always increases. Why? In order to answer this question, we must know what is Clausius inequality. To understand, let's take a heat engine with a reversible and an irreversible process. Let us take the reversible side first. If we give the work extracted on the reversible side again to the reversible process itself, it will reach the initial state without any change, and we know that the change in entropy must be zero for a reversible process. This gives us QH by TH is equal to QL reversible by TL. The total cyclic integral of entropy is equal to QH by TH minus the sum of entropy of a reversible and the irreversible process. and QH divided by TH and QL reversible by TL cancel out each other since they possess the same magnitude. We left out with minus QL irreversible divided by TL, and it is negative and lower than 0. Okay, lower than 0. For reversible process alone, the change in entropy for a cyclic process is 0. Therefore, we can say that for a cyclic integral of an entropy of a process is always lesser than or equal to 0. This is called Clausius inequality. Consider a reversible and an irreversible process as shown, and the cyclic integral is always less than 0. The cyclic integral is equal to integral of state 1 to 2 and 2 to 1. Sum of integral of state 1 to 2 and 2 to 1, and we know that the cyclic integral is always negative for irreversible process, and solving will result in the change of entropy. Change of entropy is always greater than or equal to 0. 0, the cases are the 0 for reversible and greater than 0 for irreversible case. Entropy gives the direction in which the reactions takes place. Let us take the same ice example. Assume 20 joules of energy has been lost by ice. Since the surrounding gains 20 joules, the entropy for surrounding is 20 divided by 273 plus 24 Kelvin and minus 20 divided by 273 since the ice lost energy. And the change in entropy comes to be negative, which is impossible. As we know, the entropy always increases. Now, consider 20 joules of heat energy is absorbed by the ice, and the entropy and the resulting entropy is positive. Therefore, mathematically, ice is consuming heat, and it is true. Going to the next example, consider energy flows outside the T resulting in increase in entropy, which is also true. Thank you for watching. This is Dhyanis. See you in the next video. Stay tuned.